Good afternoon. Welcome back. Let's talk momentum. Okay, so we are looking at chapter 7 of your conceptual physics book, this beautiful guy. And on chapter 7, we are starting on page 80 something? 86, starting on page 86, and we're going to flip through. Okay, so let's start at the beginning. And this should look really familiar from your physics everything sheet that we've already filled out about momentum and impulse. But starting on page 86, momentum equals impulse. So the amount of shove that you give something, that's the impulse, is equal to how much momentum or how much oomph it has when it's moving. Momentum is represented by P, so change of P is equal to J, which represents impulse. And then we can break those out into their equations and say mv equals ft. Mass times velocity of an object is equal to the force exerted on that object times the time that we're exerting that force for. All right, so let's take a look at a few examples of what that looks like. So here we have three sets of things that are occurring. So in the first one, I have a car, an orange car here, that is coming in real fast. It has a big V, meaning there's a lot of velocity, and it's coming in and about to hit a hay bale. As it hits the hay bale for a long period of time, right? It goes through the hay bale and slowly slows down. So there's a really big T, big time, which means there's not very much force on the vehicle. And so you can see the guy's a little bit unhappy that he crashed his car, but there's no real damage done to the car. Because it has a really large time, the force component can be small, right? Mass times velocity equals force times time. Okay, so let's say you hit something that doesn't give as easily as a hay bale. I'm still coming in with a big velocity. It's the same kind of car coming in at the same speed, but then it hits a wall. Well, the wall doesn't let it slow down over a long period of the time. The wall slows it down in a very small period of time. So I've got a little bitty t, which means a big force. And you can see due to that big force, the car did not do very well. It got all crushed up. This could also be applied to something like boxing, where the boxer can be really intentional about how he moves his head to minimize the force on his head from a punch. So you guys might have heard of Muhammad Ali. He was a boxer, and he had this thing that was like float like a butterfly, sting like a bee. The reason that he was floating like a butterfly, he was really soft on his feet, moving back and forth. So if somebody punched towards him, he would move his head away at the same time. They're still going to make contact with his head, but they're going to make contact for a longer period of time. And that bigger period of time means there's going to be a smaller force on his face. So the boxer's pretty happy here. He's getting punched, but it's for a big period of time, so not a big deal. As opposed to if he's moving his head in towards the punch, boom, now the punch is hitting him for just a small period of time, and that's going to lead to a big force, and he's not going to feel so good. All right. So similar idea is the concept of bouncing. If an object comes in and it has a certain momentum, demonstrated here in red, it's got the mass times the velocity, and then it just hits the ground and sticks. It went from momentum down, here we go, from momentum down to no momentum, right? From down to stopped. Okay, so that's a change of 1 times, right? Down to nothing. If it bounces, then it went from down to back up. So that's a change of 1 negative to 1 positive, or a change of 2 total. So that bounce has the down component plus the up component. So when an object bounces, it has twice as much change of velocity, which means twice as much change of momentum, which means a much bigger impulse. So if something bounces, it exerts a bigger impulse and thus a bigger force on the object that it's bouncing from. So bouncing will do much more force than just sitting and sticking. Conservation of momentum. Conservation of momentum is the idea that the momentum before a collision is equal to the momentum after a collision. We added something on your physics everything sheet for this, so I would check your physics everything sheet. Basically, it just says the momentum before the collision is equal to the momentum after the collision, and we had a special equation for that. M1I V1I plus M2I V2I equals M1F V1F plus M2F V2F. So basically, I've made blue object 1, I've made red object 2, I've made I initial before the collision green, and I've made purple after the collision final. So that way I'm separating all of my different parts, and then I can just see what's the momentum excuse me, before and after the collision for each of those objects, and make sure that all the momentum before is equal to all of the momentum afterwards. All right, so it turns out there are two types of collisions. There's what we call an elastic collision, and an elastic collision is a full bounce. So in an elastic collision, a full bounce kind of collision, all kinetic energy is conserved. And all of the energy is able to be conserved because in a full and complete bounce, there is no heat, no thermal energy created, and no friction. If it fully bounces, there's no deformation of the object, deforming it, like squishing it and then squishing it back. It's just complete and utter bouncing. So no friction, no heat, meaning all energy is conserved. All mechanical energy or all kinetic energy is conserved. So that's elastic. And that actually happens less with like elastic rubber balls and more with like steel. Steel is pretty elastic against other steel. It's not 100% fully elastic, but it's close to fully elastic. Actually, in the real world, there would be almost nothing that is fully elastic because friction always exists. You're always going to lose some small percentage to heat, even if it's an almost perfectly elastic collision. So in your physics textbook in Magic Happy Physics Land, it'll talk about 100% elastic collisions. In the real world, nothing's ever 100% fully elastic. All right, so what happens there? We have, before the collision, the white ball here is sitting still. The red ball is coming in towards it. They collide, and then the red ball sits still, and the white ball is doing all the moving. So all of the momentum from the red ball was transferred to the white ball. So that's one option. Another option is both balls are coming towards each other from opposite directions, like this. They collide, and then they bounce off each other and go back the opposite direction. So they're coming in together, bounce, and then away they go. And then the other one is, what if they're both going in the same direction, but they're both moving? Well, the red ball is coming in like a rear end collision. The white ball is going slower. The red ball is going to hit the white ball from behind right there. And now the white ball is going to take off faster, and the red ball is going to be going a little bit slower. So some of the momentum from the red ball was transferred to the white ball, and the total momentum before equals the total momentum after. Okay, so that's for a fully elastic collision. The other type of collision is called an inelastic collision. In an inelastic collision, this is what we're going to call like a full stick kind of collision. So the two objects are going to come together and they are going to fully stick together. So they become like one combined object. Basically, we're going to add their masses together when they collide and stick. So you could think of this like clay balls. Two clay balls come together and stick together. Another great example is train cars, because they have latches on each other. So they actually like intentionally latch together and stick together. So it's going to be a full stick. Kinetic energy is not conserved in this case because you lose a lot of energy to heat and friction. So you have a loss of energy due to heat, deformation of the object, friction, etc. Momentum is conserved. Momentum is always conserved in all collisions. So momentum is conserved no matter what. Energy only conserved if it is an elastic collision. Okay, So for an inelastic collision, I have two train cars that are both identical here, except different colors, but otherwise same mass, what have you. One's sitting still, the other one's coming in at 4 meters per second. They connect together. Now they have twice the mass, so their speed is going to get cut in half. So the total speed between them is going to be 2 meters per second. So I have the same amount of momentum before the collision and after the collision. Before the collision, I had 4 meters per second on one train car. After the collision, I have 2 meters per second on two train cars for a total of 4. So again, it works out as a conservation of momentum, but not a conservation of kinetic energy because it lost some to that whap right there where they collided and stuck. All right, so that is chapter 7, Momentum and Impulse, and you are now ready to hit those practice problems, which are on page 100. So go ahead and get started on those practice problems, and I will post a key for you once they are due. Best of luck.